Hello, this is Mr. Ferguson. This is video 6.2 where we talk about polar and nonpolar bonds. The goals for this lesson are to use electronegativity to predict bond types, to compare and contrast properties of polar and nonpolar substances, and then to describe two other kinds of bonding that we don't get into quite as much as we do the straight up covalent and the ionic. That would be a covalent network substance, describe that and give examples, and to recognize the properties of metallic bonds. So let's get started.
Alright, so what we're looking at here is a modified version of page 5. If you look at page 5 in your packet, you'll see the exact same thing. This is an electronegativity chart. And this is the tool we have to use to figure out what type of bond we have, either covalent, ionic, or polar or nonpolar bonds. And this is the key tool, and you'll get this on a test or quizzes when we do it.
So let's notice that the definite trend is, like we learned, the electronegativity increases the higher you are on the periodic table and the further to the right, with the exception of the noble gases, which you notice are over there. They don't have any electronegativity at all because they already have a stable configuration of electrons.
Yeah.
So what are these numbers, or kind of a ranking system? What does it rank, Mr. Hunter?
Well, the numbers are just kind of an arbitrary number given for electronegativity. They took francium and made it not francium, they took fluorine and made it the highest at 4, and then they took francium, so francium's not even shown down here, but francium is almost 0, but they wouldn't make a 0 because they don't know if they're ever going to find more stable.
So it's a ranking system for the atom pull for electrons on other atoms.
Yeah, so we know fluorine becomes negative 1.
The bigger the number, the harder it pulls on someone else's electrons.
If you notice, the ones that form negative ones have a higher electronegativity. The ones that form positive here have a pretty low electronegativity, which makes sense. So let's go on and do some practice and talk about some properties.
So we're going to talk about the rules for how you determine what sort of a bond it's going to be. And what this symbol is right here is a delta. And we use the delta symbol to represent change in something. So the delta EN is kind of our shorthand for change in electronegativity, or electronegativity difference would be another way to say it. So as we go through, if you get two elements, you say, okay, what kind of bond would they form? Well, you look up their electronegativities on that table and you find the difference. Subtract them. Just take the bigger one and subtract off the smaller one.
Exactly.
And we're going to see what the difference is. If the difference is less than 0.5, then
nonpolar covalent bond.
This is called so what this means is there's kind of equal sharing.
Yeah, equal sharing indeed. Now the next one is if you have a difference of 0.5 to 1.6, these would be known as your covalent, or your polar covalent bonds. And the polar means there are poles. And what that means is there's a slightly positive end of the molecule and a slightly negative end of the molecule. And these are the most common polar covalent thing we can think about is water. But we'll talk about this and show you why later.
So they're sharing the electrons, but it's not equal sharing. It's unequal.
Yeah,
so
make sure you copy that in.
But it's unequal. So the one atom pulls harder on the electrons than the other one, so it's got a little more of a negativity to it. Almost like a negative ion, but not quite. The other one doesn't have the electrons held as tightly to it, so it's almost like a positive ion, but not quite, so we call it a polar bond.
And then lastly here, if your difference is greater than 0.2, that makes it ionic. And we've already talked about ionic. That is, of course, when you have a transfer of electrons to make ions. That's why it's ionic. You get the positive, you get the negative, and this is normally the far left combined with some non-metal on the right, and that's when you get your ionics. You know, you got your sodium chloride, your lithium bromide, all those.
All the ones we just talked about.
Yeah.
Now that leaves us kind of a gray area there between the 1.6 and 2.0.
Yeah, these ones will come up. Most ones you have to watch out for in that area are actually your carbons with hydrogens. Your carbon-hydrogen bond, I think, somewhere near 1.6, 1.8. which before in some books could be ionic, but we know for certainty that carbon and
Not
hydrogen
ionic,
is
right.
is usually a nonpolar bond, but it's a covalent bond at least.
So what we're going to do is say it's considered ionic if you're in this range, if one of these two atoms is a metal.
So if let's say if it was, I don't know if you can get a good range for this quickly, but no, I really can't give you a good one. So let's say it was gold and fluorine. That's 1.6. So
Okay.
so if it's A, U with F, the difference I believe is approximately 1.6. That would be a metal to a non-metal, and that would give you...
That's an ionic bond.
That would be your ionic bond because it's a gold to a non-metal.
But
And the first one for carbon, it's 2.5, and hydrogen is 2.1. So it's only a 0.4. So yeah. Anyway, but
Fluorine and hydrogen would be a
or
1.9.
boron and fluorine, for example, would be a good one. Boron and fluorine actually is a difference of 2. It's actually still considered a very polar covalent bond. So I mean, it's just like I said, these are general guidelines. They're not strict rules.
Right, and different textbooks will print it different ways, but basically, if the electronegativity difference is 0 or close to 0, it's a nonpolar bond.
Exactly.
If it's really high, 2 or above, it's ionic, and if it's in the middle, it's probably a polar covalent.
Okay, let's take a look at the next slide.
So here we are, we're going to compare the properties of substances put together with the different kinds of covalent bonds. Polar versus nonpolar covalent.
You should write these down as well, of course.
Yeah, it's going to be like a T-chart.
Yeah. So first off, they're not exactly lined up, but there we go. Polar covalents usually have a higher melting point, while nonpolar covalents have your lower melting point. And then you have a higher boiling point for your polars and a lower boiling point for your nonpolars. There's a reason for that, by the way. It comes down later. Can dissolve polars and polar compounds and ionics, while the nonpolars can only dissolve nonpolars.
The rule we always use is like dissolves like. So things that are similar will dissolve things that are like themselves.
All right, the next one. Won't mix with nonpolar. So, like as we said, like dissolves like. So if it's a polar to nonpolar, they will not mix.
Did you ever drop a piece of candle wax in a glass of water?
Or oil and water. They don't separate.
Oil and candle wax are both completely nonpolar. They just will not mix with the polar water.
All right. And then for nonpolar, they're usually gases, and they're more volatile than others. So more volatile than the polar ones. Polar covalent have stronger intermolecular forces, aka hydrogen bonding. While nonpolar have these weaker intermolecular forces. And due to that, it causes the ones that have a stronger intermolecular to have higher melting points and higher boiling points.
It takes more energy to force the molecules away from each other.
And then the weaker intermolecular forces, of course, have a lower melting point or a lower boiling point.
So these are going to tend to be gases at lower temperatures than those polar covalents would be.
And then last couple here, usually a solid or a liquid if you're polar, and of course they are less volatile than nonpolar. If you didn't get all these copied, I'd suggest pausing now, copying them down, and then move on to the next slide with us.
So we're going to work a couple of example problems where we start with the formula and we are going to see if we can use electronegativity to predict what kind of bond holds this compound together.
All right, so the first one is sodium sulfide. Let's look at sodium. You can see it right here. It's 0.9. And then sulfide is over here, has 2.5. So as we said, you subtract the larger one, 2.5, from sodium's 0.9.
That's 1.4.
1.4. And that difference right there indicates to us that it would be, well, technically I guess it would be a polar covalent. But we have to apply that rule. We know that this is a metal, this is a non-metal, so we pretty much know it's an ionic. So this is where I use this one because it kind of bends the rules a little bit. You have to know when,
if there's a metal involved,
it's usually
a
ionic.
non-metal, it's almost always going to be an ionic. And this isn't actually all the way up to 1.6 like we said, but it's pretty close.
It's in that
so
range.
These are more like sort of fuzzy lines than hard and fast rules.
Yeah, so this is a good example of when you have to use your common sense over the hard and fast rules. The next one here is nitrogen and oxygen. So there's nitrogen, there's oxygen.
And by the way, it doesn't matter if there's any subscripts. We're just going to use the formula for the element. You know, just that 3.5 is the number for nitrogen, minus 3, which is the number for oxygen.
So we do these subtractions. We find out it's equal to 0.5, and that's
that would be right at the sort of high end of the non-polar range.
Yeah, so it would be non-polar for this one. You heard that high-pitched girly laugh in the background about 30 seconds ago. That was Ben. You can say hi later about that. So we're going to have more practice with this later in our worksheets and our packets, of course. So if you don't understand it, just turn to a page in our packets and just kind of work through some. But we will work through more together in class. All right, so we're going to not spend a lot of time on these ones, but the metallic bond is, as it sounds, it is made of metals.
It's usually like a whole bunch of the same metal atom all together.
Yeah, so the first thing we're going to talk about is something known as the, excuse my handwriting, sea of electrons. What does that mean? Well, think about it. All these spheres are going to be the nuclei of some metal, and they're going to have these electrons out here kind of free-flowing and free-moving between all of them. So they're not really stuck to any one nucleus. They're kind of,
those outer valence electrons don't belong to any one atom.
That's why they're a sea. They move about. So what does that also give us? That gives us the ability to have good conductivity. So of course metals conduct. So you don't want to put a fork in a light socket because you'll shock yourself. They are malleable.
Because again, the ions can rearrange and the electrons will still hold them together, but they're able to change their relationship. It's not like in an ionic crystal where they have to stay locked in this exact position or the whole thing falls apart.
So they're hard, but not, well, they're usually hard usually, but they are not usually brittle. So think of steel. You hit steel, it will bend, but it won't break. So it's hard, but not brittle. And then they are also not brittle. And I honestly don't think there's much more about this right now we want to talk about, but they are metal to metal bonds. It's the last thing for this.
So the last type of bonding we're going to talk about really isn't a different kind of bond. It's just kind of a special case of one of the kinds of bonds. It's called a covalent network. So everybody, I would guess, that's listening to this, if we ask you what's the hardest substance known,
I would say a
probably
diamond.
be able to say diamond. And diamond is a really good example of a covalent network bond. So diamond is pure carbon, and probably you knew that already. Carbon really likes to form covalent bonds. And in fact, because carbon has 4 valence electrons, and it needs to share its 4 valence electrons to get 4 more, carbon will almost always form a total of 4 covalent bonds, 4 single bonds with other things around it.
And in this case, it's actually kind of like a pyramidal shape as well. They kind of feel sort of a pyramid, I guess, is the way to talk about it.
Which I can't draw it in 3D, but basically if you picture every carbon atom
linked
is bonded
together with
with
4 other
carbon atoms as far as the eye can see.
They can be very tight-knit and hard to break apart. So, they're usually very hard, these covalent networks.
So the classic example would be a diamond.
And I think also silicate or sand.
Silicate, like sand is made of.
But that's not as hard as
it's
diamond.
It's not pure carbon. Diamond's pure carbon.
Silicate has no carbon. It's silicon and oxygen.
Covalent.
And they only form 2 or so
bonds in all directions.
Yeah. So that means it's always going to be non-metal to non-metal bonds for a long time. Other covalent networks you might think of would be plastics, for example, but they have a different type of, So these are very broad. They're very difficult to fully understand, but just know it's covalent bonds in all directions.
Extremely hard.
Well, that's for diamonds. Again, plastics aren't extremely hard, and they are also in a covalent network.
Tough and resilient materials tend to be non-conductors. although
They can.
they can.
Graphite, for example.
So it's sort of a special case, and there's some unique materials that have some unique properties that fall into
But
this
the key
category.
term, covalent bonds in all directions. And that's about all we want you to really pick up on this one. I believe we're done for now, and we'll
Okay.
review later. Bye.